Hi, welcome back to chemistry. You're here with Mrs. Mays, and today we're looking at the concentration of solutions. Let's get started. First, let's define some broad types of solutions. The first type is simply called a saturated solution. Saturated solutions contain the maximum quantity of solute that could be dissolved in that particular solvent at that temperature. Wow, can you read my writing? Maximum amount of solute. So that's what a saturated solution is. There's also such a thing as an unsaturated solution. Unsaturated solutions contain less than the maximum amount of solute that could dissolve in that particular solvent at that particular temperature. And finally, your last category is considered to be a supersaturated solution. Supersaturated solutions would contain more than the normally allowable solute. So more than the maximum solute that could typically dissolve in that solvent at that temperature. Now let's be more specific. There are a couple of different ways that we could express concentration, but by that word concentration, what we mean is just describing the amount of solute that is dissolved in a specific quantity of solvent at a given temperature. Oops, I'm doing it wrong. Concentration amounts can be expressed as a percent, which is most common, and here we might do percent by volume or percent by mass. Those are both rather common ways to express it. Another thing we might use for larger scale solutions, like at a water treatment facility, in industry, or a swimming pool or something, we would call it parts per million. ppm stands for parts per million. And for something that exists in a greater concentration, we may refer to something as parts per thousand, if it was going to be more concentrated than parts per million would express in a reasonable way. Okay, so let's see how we might do this. Here's an example of a simple percent by volume, and you may have done this before. To make orange juice, I normally take 1 can of frozen orange juice concentrate and mix it with 3 cans of water because that's what the directions say to do. So that gives me 1 can with the orange juice and 4 total cans of juice and water together. So my total solution goes in the bottom, in the denominator. So I take the part I'm interested in, I take the part that I'm interested in and divide by the whole amount, and then I turn that decimal to a percent by multiplying by 100 and putting a percent sign after it. So I would take 0.25 and turn it into a percent, which would be 25%. Seems easy, right? Well, it is. It's part divided by whole amount. That's it. Now let's approach a problem that has percent by mass instead of percent by volume. So the question says, what is the concentration of each of the 3 solutions as expressed as percent sucrose by mass? I don't remember doing 2. Okay, well, 3, 2, whatever. Let's take the part that we're interested in, which is the sucrose, 17 grams, divided by the whole entire amount. So I have to add my sucrose and my water together, 17 plus 183 grams total. Now this percent, I need a calculator. So we're going to take 17 divided by, the denominator was 17 plus 183. Remember to enclose your denominator in parentheses so it all stays together. So that is 0.085. Okay, to turn my decimal to a percent, I can multiply by 100, or I can move the decimal twice, and I get 8.5% of my solution is sucrose. Let's look at another problem that's very similar. Here I've got 30 grams of sucrose that dissolves in 300 grams of water. So I take the sucrose, which is my solute, divide by the mass of the total solution. So 30 plus 300 from the water gives me 330. So let's figure out what is 30 divided by 330, and we'll convert that to a percent. So my calculator comes back. Point 0.09090909. We don't need all of those, only some. Looks like 3 sig figs is what we need, so 0.0909. How do I make this a percent? Well, I can multiply by 100, or I can just move the decimal over 2 times, and I've got my percent. 9.09% of my solution is sucrose. And that's how we would do percent by mass. Parts per million takes a similar approach. So I would take my 0.20 grams of iron, or 0.002 that is, and that's iron 3 ions, and then divide that by the total amount. Whoops, I didn't get that total amount. 500 grams of water. Oh, now I got to move that down. Okay, let's divide by the total amount, but notice when I add 500 grams of water to the amount 0.002, I basically get something that's really close to 500. So it's not going to make a huge difference. I'll go ahead and put it in the calculator anyway, and we'll see what we get. The part we're interested in divided by the whole amount. So I take 0.0020 divided by the whole amount plus 0.002, close the parentheses on the denominator, and I get this decimal 3.9999999. Let's round that to 4.0 times 10 to the minus 6. Okay, so I want parts per million. So if I had 1,000,000 parts, let's make this a fraction. 1,000,000 is 1 times 10 to the 6th power. So if I have 1,000,000 parts, how many of them are going to be irons? Well, this says only 4. 4 parts per million. 4 in 1,000,000 particles will be the iron 3. So we write 4 parts per million of iron 3 ions. That's called the ferric ion, not the ferrous ion. So that's how we might deal with a parts per million problem. I'm going to skip the next one because we don't use parts per million very often in this class. What we do use, however, is molarity. Molarity is a handy unit of concentration because it allows us to express the moles of the solute for every liter of solution. It's abbreviated with a capital M. So when you see a big M, then you'll be thinking molarity. We pronounce this, we would say the word molar. Remember in your copper to copper lab, we used 6 molar nitric acid. No, it was 6 molar hydrochloric acid and 6 molar sodium hydroxide. We used concentrated nitric acid, which is more like 18 molar. It's ridiculous. Something crazy. 15 molar, maybe. Yeah. So what it means is that when we say it's a 1 molar solution, what we're really saying is that we have 1 mole of our solute for every 1 liter of solution that exists. That's what molarity means. And this is the unit that we'll be using the most in chemistry class. So let's work through a problem where we would have to solve for the molarity. This one asks us to calculate the molarity of a solution with 34.6 grams of sodium chloride dissolved in 125 milliliters of solution. So first I need to know how many moles of solute do we have. Let's get the molar mass of sodium chloride. For every 1 mole of NaCl, I will need 58.5 grams of NaCl. All right, calculator time. Okay, so we take 34.6 divided by 58.5, and I get 0.591 moles of sodium chloride. But we haven't answered the question yet because my solution is 125 milliliters. So let's change milliliters to liters. We're just going to move the decimal 3 times over because milli is 1/1000th of a liter. So I move it 3 times, and I'm going to take my moles divided by my liters. That's what molarity means, how many moles per liter, right? So take the moles, 0.591 moles of sodium chloride, divide by your number of liters, which we converted from milliliters. It's 0.125 liters total solution, and we'll divide those two. So I'll take my answer in my calculator, and we're going to divide that answer by 0.125 liters, and we get a value of 4.73 molar. So our concentration is 4.73 molar sodium chloride solution. That's how we would use the molar concentration, calculating molarity by moles divided by liters. And that's all you need to know about concentration. We'll see you guys later.